The universe is a single, connected structure. It is not a collection of lonely islands, but a vast, luminous network, a cosmic skeleton binding every galaxy in a shared architecture. This is the great cosmic web, the largest thing we have ever discovered, and mapping its hidden framework is the key to unlocking the deepest secrets of existence. By the end of this journey, you will understand the fundamental forces that built our reality and see the cosmos in a way you never have before. How did this immense structure grow from almost nothing, and what unseen forces are now shaping its evolution? The answers lie in a map we are only now learning to read. What does it mean to find our place within such an immense tapestry? But to see it, we must first change how we look at the cosmos. Think of the night sky not as a flat canvas of stars, but as a deep ocean. What we see from our tiny vantage point is a mere projection, a two-dimensional snapshot of an unimaginably three-dimensional reality. If you could step outside our galaxy and fly through the darkness, the true architecture would reveal itself. You would not find galaxies scattered like confetti. Instead, you would see them gathered, pulled into immense rivers of light. These are the filaments of the cosmic web, threads of galaxies and dark matter stretching for hundreds of millions of light years. Where these mighty threads cross, they knot together into dense, brilliant clusters, the great cities of the universe. And between these luminous structures lie the voids, unimaginably vast deserts of near-nothingness, so empty that a single galaxy within one would feel profoundly alone. This web is not an accident. It is the inevitable final shape of the universe, the direct result of everything that has happened since the first moments of the Big Bang. The story begins with the tiniest of seeds, microscopic ripples in the fabric of the newborn cosmos. For billions of years, the relentless, invisible hand of gravity worked on those ripples. It gently tugged at the slightly denser patches of dark matter and gas, drawing more and more material toward them. Over cosmic time, this process sculpted the smooth, early universe into an intricate, lacy structure. The dense knots grew into galaxy clusters, the material in between stretched and thinned into the great filaments, and the emptiest regions expanded into the voids. So when we finally mapped this web, we were not just drawing a picture of where things are. We were reading a historical document, a record of the universe's entire growth, written in the positions of its galaxies. This map is our key to understanding the forces that built everything we see. But to draw it, we faced a problem of almost impossible scale. How do you chart a structure so vast it makes individual galaxies look like dust motes? The answer required a new kind of astronomy, one that could see the invisible threads holding the luminous universe together. The most spectacular highways in the universe carry no traffic you could ever see. They are the filaments, silent rivers of galaxies flowing through the darkness for distances that dwarf our entire local group of galaxies. To stand within one would be to witness a strange and beautiful architecture. Galaxies are not scattered randomly here. They align, pulled into long, graceful chains that curve across the void, following the invisible contours of something far greater. These luminous beads on a string are just the visible trace of the true structure, which is built from the mysterious dark matter that forms its skeleton. The galaxies we see are merely where ordinary matter, the gas and dust that make stars and planets, has pooled along these dark rivers like dew on a spider's web. The filaments themselves are mostly emptiness, but it is a special kind of emptiness. It is a corridor where the density of the universe is just slightly higher than the profound voids on either side. That tiny difference, amplified over billions of years by gravity's unwavering patience, was enough to sculpt these bridges. Within them flows not just galaxies, but an ocean of diffuse, hot gas that has never cooled enough to ignite into stars. This is the lost majority of the universe's ordinary matter, hiding in plain sight within the filaments, a ghostly atmosphere for the galactic cities it connects. Finding these structures was a triumph of cosmic cartography. You cannot point a telescope at a single point in the sky and see a filament. They are too vast, too faint. Their map must be pieced together statistically by plotting the precise three-dimensional positions of millions of galaxies and asking a simple question. How are they all connected? When scientists finally did this, the hidden pattern emerged from the noise. The galaxies were not isolated. They were linked in a vast, branching network, exactly as the theories of cosmic evolution had predicted. This was the moment we moved from imagining the universe's grand design to actually tracing its form, confirming that the cosmos is not just a collection of objects, but a single, growing organism. Yet the true anchors of this cosmic architecture are not the silent filaments, but the spectacular cities that form where they meet. At the intersections of these great highways, gravity has woven the most densely packed communities in the known universe. These are the nodes, the galactic metropolises, where thousands of galaxies are gathered into a single, swirling metropolis bound by an immense and unifying force. If a filament is a quiet country road, a node is like a brilliant central square, a place of constant, vibrant motion and radiant light. Consider a place like the Coma cluster, a node located hundreds of millions of light years away. Here, not dozens but thousands of galaxies all orbit a common center, held within a gravitational embrace so profound that their paths are forever intertwined. The environment within a node is intensely dynamic and transformative. Galaxies do not simply drift past one another. They interact, they gently tug at each other's spiral arms with tidal forces, and over spans of billions of years, they often draw together and combine. These monumental unions can reshape delicate spiral structures, guiding stars into new, smoother forms. This is how the universe creates its giant elliptical galaxies, the vast, rounded shapes that come to dominate these dense urban centers. The node is a galactic workshop where the form of individual galaxies is reshaped by the profound influence of their community. For astronomers, these brilliant clusters are the most visible parts of the cosmic web to find. Their incredible concentration of stars and hot gas makes them shine across the electromagnetic spectrum, acting as luminous landmarks in the dark, but their true importance extends far beyond their light. A node is not just a collection of galaxies, it is a profound focal point in the fabric of space-time, a gravitational cornerstone. The depth and shape of this focal point are dictated primarily by the vast, unseen halo of dark matter that cradles the entire cluster. By studying how galaxies move within the node and how the hot gas between them behaves, scientists can measure this invisible anchor. They can weigh the gravitational presence that not only holds the metropolis together but that also shaped the very filaments that connect to it. In this way, each brilliant node acts as a key reference point on our map, a place where we can directly explore the dark matter framework that the entire visible universe is arranged upon. The story of the cosmic web is written in the quiet filaments, but it finds its boldest expression in these dazzling, dynamic metropolises. Yet for every brilliant metropolis and luminous thread, there exists its opposite in the cosmic architecture. Between the crowded highways and glittering cities lie the voids, the great cosmic deserts. These are regions of staggering emptiness, so vast that a single galaxy drifting within one would see only darkness in every direction for distances exceeding hundreds of millions of light years. If the filaments are rivers and the nodes are cities, then the voids are the continents of quiet that separate them, defining the negative space that gives the web its distinct, sponge-like structure. They are not truly empty, of course. Within them floats an unimaginably thin haze of hydrogen gas, and on very rare occasions, a lonely, isolated galaxy. But their defining feature is their profound lack, a density of matter so low it highlights the incredible contrast of the universe. This spaciousness is not a flaw in the design, but a fundamental feature of its history. Remember those tiny ripples from the universe's birth. The voids are the legacy of the lowest points in those ripples, the regions where there was just slightly less material to begin with. Over billions of years, gravity acted like a cosmic organizer, drawing matter away from these underpopulated areas and into the denser filaments and nodes. The voids were left behind, growing more spacious as the web condensed around them. In a very real sense, the universe grew its structure by clearing these territories. But within their quiet expanse lies a crucial clue to one of the greatest modern mysteries. The boundaries of these voids, where their near-nothingness meets the dense walls of the cosmic web, are where the effects of dark energy are most pronounced. Dark energy is the mysterious repulsive force that is causing the expansion of the universe to accelerate. In the dense knots of the web, gravity's pull is strong, holding its own against this cosmic push. But in the voids where gravity's grip is weakest, dark energy finds little resistance. These great deserts are not static, they are stretching and growing faster than the rest of the cosmos. By meticulously mapping the shapes and sizes of voids and measuring how their boundaries evolve over cosmic time, astronomers can take the universe's pulse. They can see the imprint of dark energy's push on the largest scales, using spaciousness itself as a measuring tool. The story of the cosmic web is told not only by where the light is, but by where it is not. In the profound silence of the voids, we listen for the whisper of the force that will ultimately shape the fate of everything. The brilliant galaxies and vast empty voids are only the visible expression of a deeper reality. To understand the cosmic web, we must confront a simple, astonishing fact. Everything you have ever seen, every star, every planet, every person, is made from a rare and special kind of substance. It is the minority ingredient in the cosmic recipe. The overwhelming majority of the material in the universe is something else entirely, a presence that permeates the darkness. We call it dark matter, and it is the invisible architect of everything. This mysterious substance does not shine, reflect, or absorb light in any way we can detect. It is completely transparent. We cannot see it, but we know it is there because of its immense gravitational influence. Think of it like the wind. You cannot see the wind itself, but you can watch it shape the dunes of a desert. You can feel it bend the branches of a tree. Dark matter is the cosmic wind, and the entire structure of the universe is bending to its will. Based on the most precise measurements we have, this invisible material makes up roughly 85% of all the matter in existence. The ordinary atoms that build our world, known to scientists as baryonic matter, are just the remaining 15%, a luminous frosting spread across a much larger unseen foundation. This distribution changed the entire story of cosmic evolution. In the early universe, dark matter was already gathering together under its own gravity, forming an immense invisible framework. This framework acted as a gravitational scaffold, a skeleton upon which the ordinary gas could later collect. Where the dark matter was densest, its pull was strongest, drawing in clouds of hydrogen and helium. Only then, within these concentrated pools of normal matter, could the first stars and galaxies ignite. So the glorious network of light we map today, the filaments and nodes, did not form first. They settled into place following the blueprint laid down by the dark matter. The galaxies we use as tracers are like streetlights on a highway. The streetlights show you the path of the road, but the road itself, the solid bed beneath, is the dark matter. Without this immense unseen foundation, gravity would have been far too weak to gather material so efficiently. the universe would likely be a much smoother, far more quiet place, a diffuse and lonely sea of gas with few, if any, brilliant islands of stars. Therefore, every map of the cosmic web is at its heart a map of dark matter. When astronomers painstakingly chart the three-dimensional positions of millions of galaxies, they are not just plotting points of light. They are using those luminous points as markers to trace the contours of the invisible mass that holds them. They are reading the impression of the true structure. By measuring how galaxies move within clusters, or how their light is bent by gravitational lensing as it travels to us, scientists can weigh the unseen halos that surround them. They can measure the gravitational valleys and mountains of the dark matter landscape. This turns our understanding inside out. We are not studying the web to learn about galaxies. We are studying galaxies to learn about the web, and we are studying the web to finally understand the mysterious invisible substance that dictated its form. The cosmic web is the most dramatic evidence we have that our universe is shaped by something we cannot see, a silent partner in the construction of everything that exists. But a cosmic architecture this grand is not static. It is caught in a slow, titanic struggle between two opposing forces. The dark matter scaffold, with its immense gravitational pull, works tirelessly to draw the web tighter, to condense its filaments and enrich its nodes. Yet acting against this cohesive force is something far more mysterious, a presence that permeates the very vacuum of space itself. This is dark energy, and its role is not to build but to stretch. It is the engine of the universe's accelerating expansion, a gentle but relentless repulsive force that pushes the very fabric of space-time apart. While gravity works locally to gather matter, dark energy works globally to create more space between everything. This creates a fundamental tension that is now shaping the evolution of the entire cosmic web. You can think of it as a vast, slow-motion tug of war on the largest scale imaginable. In the dense urban centers of the galaxy clusters, gravity's grip is still dominant. These massive knots hold their shape, bound tightly by their own immense weight. But in the spacious territories between them, the story is different. Within the great cosmic voids, where matter is sparse and gravity's pull is weakest, dark energy meets little resistance. These empty regions are not merely sitting there. They are expanding faster than the rest of the universe, their boundaries stretching, causing the walls of galaxies that surround them to thin and become more diffuse. Over billions of years, this relentless push makes the filaments of the web, those great luminous highways, stretch and grow fainter as the galaxies within them are pulled farther apart. It acts as a kind of cosmic brake on the formation of new, grand structures. Where gravity might have once drawn together two distant filaments to form a new, massive node in the far future, dark energy's push may now prevent that union from ever happening. The universe's construction phase, driven by gravity, is gradually giving way to an era of stretching, driven by this enigmatic force. This makes the cosmic web more than just a map of where things are. It becomes a living history book and a crystal ball. By meticulously measuring how the web has changed over cosmic time, astronomers have a direct test for the nature of dark energy itself. Does its strength remain constant, or does it vary? By comparing the web's structure from when the universe was half its current age to how it appears today, scientists can see the imprint of dark energy's push on the largest canvas possible. They can measure how quickly the voids are growing and how the threads between galaxies are straining. Each subtle change in the web's architecture is a clue, helping us understand the force that will dictate the ultimate fate of everything. The story of the cosmic web is therefore the story of this great competition. It is the visible record of a balance between the pull that builds our home and the push that will one day determine its final shape. The very architecture of the universe was written at the beginning of time. To understand the web, we must travel back to the first unimaginably fleeting moments after the Big Bang, to a cosmos that was not yet filled with stars or galaxies or even atoms. It was a seething, hot, and perfectly smooth ocean of pure energy, yet within that smoothness, at the tiniest quantum level, a fundamental uncertainty was at play. Empty space itself was not perfectly still, but fizzing with microscopic fluctuations. Think of it like the surface of a perfectly calm pond on a subatomic scale, where random, tiny ripples constantly appear and vanish. These were quantum ripples in the fabric of reality itself, fluctuations in the density of the primordial energy field. For a story that spans hundreds of millions of light years, it is astonishing that it hinges on events so small. Then something extraordinary happened. The universe underwent a period of hyper-accelerated expansion known as inflation, stretching faster than the speed of light in a fraction of a second. This expansion did not create those quantum ripples, but it did something just as important. It stretched them. Those random, microscopic wrinkles in the newborn cosmos were blown up to cosmic proportions, frozen into the fabric of space as it expanded. The tiny became immense. Where there was a slightly denser patch of energy, it became a region spanning light years that was ever so slightly more dense than its surroundings. Where there was a slightly emptier patch, it became a vast underdense region. This process imprinted a specific pattern, a kind of cosmic fingerprint, across the entire observable universe. The pattern was not one of sharp edges or clear shapes, but a gentle, statistical distribution of hills and valleys in the density of matter and energy. After inflation ended and the universe cooled, ordinary matter, primarily hydrogen and helium, formed from that energy, and it did not form uniformly. It naturally pooled into those regions of slightly higher density that inflation had created. These overdensities, these hills in the cosmic landscape, were the seeds. They were the starting points. For the next 13.8 billion years, the relentless, patient force of gravity took over. It gently pulled more and more material, both the invisible dark matter and the ordinary gas, toward these seeds. The slightly denser regions became denser still, growing like snowballs rolling down a hill, gathering mass. Over cosmic time, the highest peaks grew into the brilliant galaxy clusters, the nodes of our web. The ridges between them stretched into the great filaments, and the deepest valleys, the underdense regions, expanded into the vast, empty voids. This means the intricate, lace-like structure we map today, with its great walls and spacious deserts, is not a random accident. It is the direct, grown-up version of that initial pattern imprinted during inflation. The cosmic web is a preserved impression of the universe's first moments, magnified to a scale we can finally see. This connection is why mapping the web is so much more than making a chart of galaxies. It is a form of cosmic archaeology. By meticulously measuring the distances between galaxy clusters, the thickness of filaments, and the sizes of voids, cosmologists are essentially measuring the properties of those original quantum ripples. They are reading the opening lines of the universe's story. The geometry of the web, its specific statistical pattern, serves as a powerful test for our theories of the Big Bang and inflation. Did inflation happen exactly as we think? What was the energy of that primordial field? The answers are not found only by looking back at the faint glow of the cosmic microwave background, the afterimage of the Big Bang. They are also found by looking at the present-day structure that glow eventually became. The web is a bridge connecting the quantum physics of the universe's birth to the grand astronomy of its maturity. In its filaments and voids, we see the echo of a whisper from the beginning of everything. These profound connections between the quantum dawn and the present-day web are not just theoretical. We can watch them unfold. To study a structure as immense and ancient as the cosmic web, we cannot run experiments in a traditional lab. We cannot rewind time. Instead, we build a new kind of laboratory, one constructed not from steel and glass, but from pure mathematics and raw computational power. This is the world of cosmological simulation, where we attempt to grow a universe inside a supercomputer. The process begins with a set of ingredients and a recipe based on our best physical laws. Scientists start with a virtual box of space, representing a chunk of the early universe just after the Big Bang. They fill it with a digital grid representing dark matter and gas, seeding it with those tiny primordial ripples we discussed. Then they program in the fundamental forces. The relentless pull of gravity, the complex hydrodynamics of gas cooling and heating, the explosive feedback from supernova and black holes, and even the subtle push of dark energy. With all these rules in place, they press a digital play button and let the simulation run. What unfolds over weeks of supercomputer time is a breathtaking accelerated movie of cosmic evolution. You can watch as gravity begins its patient work, pulling the dark matter into a faint, ghostly web. You see the ordinary gas flow along those invisible filaments, pooling at the intersections. In those dense knots, the first virtual galaxies spark to life, their stars living their cycles, enriching the cosmos with new elements. Over billions of simulated years, the entire intricate architecture of the cosmic web emerges spontaneously from the code. Projects with names like Illustris TNG and the Millennium Run have produced these staggeringly detailed virtual universes, each containing millions of simulated galaxies within a digital space hundreds of millions of light-years across. The true power of these simulations is not just in their visual splendor, but in their predictive power. When scientists compare the final structure of their simulated cosmic web to the painstakingly observed maps of our real universe, the agreement is nothing short of remarkable. The statistics match. The way galaxies cluster along filaments, the sizes and shapes of voids, the distribution of massive clusters, all align with what our telescopes see. This agreement is a profound validation. It tells us that our understanding of the basic ingredients and rules of the cosmos, from dark matter's scaffolding to dark energy's push, is essentially correct. The simulation is a test, and the real universe is passing it. But these digital laboratories do more than confirm what we know. They let us ask what if. What if dark energy were slightly stronger? What if dark matter particles interacted with each other in a different way? By tweaking the initial parameters and running the simulation again, researchers can see how the cosmic web would change. They can compare those alternative outcomes to our observations, ruling out some theories and refining others. In this way, every new, deeper map of the real cosmic web acts as a guide, helping us adjust the recipe of our simulations to better reflect reality. It is a continuous conversation between the digital and the actual, a process of using virtual universes to decode our own. These simulations are more than just models. They are a form of time travel, allowing us to witness the grand billion-year dance that led to our place in the tapestry. Our digital reconstructions are only as good as the real-world data that guides them. To map the actual cosmic web, astronomers must become cartographers of the invisible, employing ingenious techniques to trace a structure that defies simple observation. The challenge is immense. You cannot simply point a telescope at the sky and photograph the web. Its filaments are too faint, its scale too grand. Instead, scientists must piece the map together indirectly, using clever methods to find the hidden architecture between the points of light. One of the most powerful approaches is the Monumental Galaxy Survey. Projects like the Sloan Digital Sky Survey have undertaken a cosmic census of staggering proportions. Using dedicated telescopes, they do not just take pretty pictures, they systematically scan vast swaths of the sky, capturing the light from millions upon millions of galaxies. For each galaxy, they measure not only its position on the two-dimensional sky, but crucially, its distance from us. They achieve this by analyzing the galaxy's light spectrum. As the universe expands, the light from distant galaxies is stretched, shifting its color toward the red end of the spectrum. By measuring this redshift, astronomers can calculate how far away the galaxy is and thus place it in three-dimensional space. Imagine trying to map a vast, dark forest at night by only looking at the fireflies within it. You would note the position of each tiny spark. If you could also measure how far away each firefly was, you could start to see patterns. You might notice they are not scattered randomly, but clustered along the branches of unseen trees, tracing the hidden structure of the forest itself. This is what a galaxy survey does on a cosmic scale. By plotting the precise three-dimensional locations of millions of galactic fireflies, the hidden pattern of the web emerges statistically from the noise. The galaxies trace out the dense walls and filaments, revealing the luminous skeleton of the universe. This method excels at mapping the web's most prominent features, the brilliant nodes and the thick strands where galaxies congregate. But galaxies are only part of the story. The filaments themselves are filled with a diffuse, hot gas that rarely ignites into stars. To map this elusive component, astronomers use a different, even more subtle technique. They turn to the universe's most brilliant lighthouses, quasars. These are the intensely luminous cores of distant galaxies, powered by supermassive black holes. As the piercing light from a quasar travels across billions of light years to reach us, it passes through the faint hydrogen gas that permeates the cosmic web. This gas does not emit its own light, but it leaves a fingerprint. Specific wavelengths in the quasar's light are absorbed by the hydrogen atoms it encounters along the way. The result is a quasar's spectrum, which should be a smooth curve of light, becomes notched with thousands of narrow, dark absorption lines. Each line corresponds to a specific cloud or filament of hydrogen gas at a specific distance. Because this pattern resembles a dense forest of lines, scientists call it the Lyman alpha forest. By studying this forest in the light of many quasars, astronomers can reconstruct the distribution of this invisible intergalactic gas. It is like using a network of distant spotlights to cast shadows of the invisible material in front of them. This method probes the web's diffuse interior, the material in the filaments that galaxy surveys cannot directly see. Together, these techniques provide complementary views. Galaxy surveys map the sparkling cities and major highways. The Lyman alpha forest maps the atmosphere, the thin, hot gas that fills the space between them. Each is a piece of the puzzle, and when combined, they give us our most complete portrait yet of the cosmic web's full anatomy. This is not a single snapshot, but a layered, painstaking reconstruction, built from the light of millions of galaxies and the subtle shadows cast on the beams of quasars. It is how we learn to see the unseeable, transforming raw data into a map of the largest structure in existence. The light from a quasar is a cosmic message in a bottle. After traveling for billions of years, it arrives at our telescopes carrying not just the story of its brilliant origin, but a detailed record of every cloud and wisp of matter it encountered on its epic journey. This is the key to a technique that feels almost like magic. When this piercing beam of light passes through a cloud of neutral hydrogen gas, the most common element in the universe, something specific happens. The hydrogen atoms are tuned to absorb a very particular shade of ultraviolet light, known as the Lyman alpha line. Each time the quasar's light passes through a hydrogen cloud, that specific wavelength gets plucked out, leaving a tiny, dark notch in the spectrum of the arriving light. Now consider the path this light takes. It does not travel through empty space. It weaves through the cosmic web, passing through the diffuse gas that fills the great filaments and brushes past the walls of galaxy clusters. Along a single line of sight stretching over billions of light years, the quasar's beam will intersect hundreds, even thousands of these hydrogen clouds, each at a different distance. Each cloud leaves its own unique absorption line, shifted to a different place in the spectrum based on how much the universe has stretched since the light passed through it. The result is not one dark line, but a dense, intricate thicket of them. This is the Lyman alpha forest, a beautiful and complex barcode imprinted on the quasar's light. To an astronomer, this forest is not noise. It is a treasure map. Each absorption line is a data point. Its position tells us the distance to that specific cloud of gas. The depth and width of the line reveal the density and temperature of the cloud. By meticulously decoding this forest in the light of a single quasar, scientists can reconstruct a precise, one-dimensional core sample of the universe along that singular line. It is as if they took an impossibly long measurement through the cosmos and pulled out a strand, revealing every layer of gaseous structure it passed through. But the true power emerges when this is done not for one quasar, but for hundreds, each pointing in a different direction. Imagine taking thousands of these one-dimensional core samples, each probing a different radial path through the cosmic web. By combining them all, a three-dimensional picture begins to coalesce. Regions where many lines of sight show dense absorption reveal the locations of massive filaments and the walls of great voids. This allows astronomers to map the cosmic web's gaseous skeleton in places far too faint for any galaxy to have formed, tracing the delicate veins that galaxy surveys can sometimes miss. This method provides the crucial complementary view. Galaxy surveys show us where the stars have lit up. The Lyman alpha forest shows us the raw material from which future stars might one day be born, the hidden atmosphere of the largest structure in existence. The faint absorption lines in a quasar's light give us one way to measure the universe's hidden anatomy. But there is another, even more subtle pattern woven into the fabric of the cosmic web itself, a kind of cosmic echo that serves as a perfect measuring stick. This pattern is known as Baryon acoustic oscillations, and it is a direct imprint from the universe's fiery infancy. To understand it, we must go back to a time before the first stars, when the cosmos was a searing, opaque plasma, a thick soup of light and matter. In that dense early universe, gravity was trying to pull matter together into clumps, but it faced a powerful opposing force. The intense radiation from the hot plasma created an immense outward pressure, like a constant, powerful wind pushing against gravity's pull. This created a tug of war, setting up rhythmic oscillations or sound waves that rippled outward through the primordial soup. These were genuine sound waves, but on a cosmic scale, with crests and troughs moving through the hot gas. For about 400,000 years, these pressure waves expanded outward from every slight overdensity, like ripples from a stone dropped in a pond. Then the universe cooled enough for atoms to form in an event called recombination. The opaque plasma suddenly cleared, allowing light to travel freely for the first time, creating the cosmic microwave background we observe today. At that precise moment, the sound waves froze in place. The ripples stopped moving. The material that had been gathered at the leading edge of each wave, at a very specific distance from the original center, was left there, set in a new arrangement. This created a subtle but statistically predictable preference in the universe. You would find a slightly higher number of galaxies separated by this specific scale, a distance of about 500 million light-years, than you would find at any other separation. This is the Baryon acoustic oscillation signal. It is not something you can see with your eye in an image of galaxies. It is a statistical imprint, a faint but incredibly regular pattern in the way matter is clustered. Think of it like the texture in a piece of fabric. Up close, you see individual threads woven together seemingly at random. But if you step back and analyze the whole cloth, you find a consistent, repeating pattern in the weave. The BRO signal is that consistent pattern in the cosmic tapestry. For astronomers, this preserved sound wave is a gift of immense value. It acts as a standard ruler etched across the entire sky. Because we know the physical size of this ruler from our understanding of the early universe's physics, we can use it to measure cosmic distances with phenomenal precision. By surveying millions of galaxies and measuring their clustering, scientists can detect this preferred scale at different epochs in cosmic history. They can ask, how big does this 500 million light-year ruler appear to us now, when we look at galaxies that are, say, 7 billion light-years away? The answer reveals the expansion history of the universe. If dark energy has been strong, stretching space more aggressively, that standard ruler will appear more compressed in our measurements from the past. If expansion has been slower, it will appear closer to its true size. By applying this ruler at multiple distances, we can chart exactly how the universe's expansion rate has changed over billions of years. This turns the large-scale structure of the cosmic web from a map into a precision instrument. Every filament and void becomes part of a calibration grid, allowing us to measure the strength and nature of dark energy itself. In the subtle, preserved echo of those primordial sound waves, we find one of our clearest guides to understanding the cosmos. The ultimate map of the universe is still being drawn. Our current charts, while revolutionary, are like the first rough sketches of a new continent, revealing coastlines but leaving the vast interior a mystery. The next generation of cosmic cartography is already underway, and it promises to transform those sketches into a hyper-detailed atlas of everything. A new fleet of telescopes, both in space and on the ground, is preparing for the most ambitious surveys in the history of astronomy. The European Space Agency's Euclid telescope is now in orbit, designed to measure the shapes and positions of over 1 billion galaxies across 10 billion years of cosmic history. Its primary mission is to trace the invisible web of dark matter by observing how its gravity subtly distorts the light from those distant galaxies, a phenomenon called weak gravitational lensing. By mapping this distortion across the sky, Euclid will produce the most extensive three-dimensional chart of dark matter ever made, finally letting us see the true underlying skeleton in stunning detail. Joining this effort will be NASA's Nancy Grace Roman Space Telescope, set to launch later this decade. Roman will peer even deeper into the infrared universe, capturing the light from galaxies so far away that their light has been traveling for most of cosmic time. Its wide field view is 100 times larger than that of the Hubble Space Telescope, allowing it to conduct a sweeping census at an incredible pace. It will hunt for the subtle imprint of Baryon acoustic oscillations, those frozen sound waves from the early universe across an unprecedented volume of space. By measuring how this standard ruler appears at different epochs, Roman will deliver the most precise measurement yet of how dark energy has stretched the cosmos over billions of years, testing whether its strength has remained constant or changed. On the ground in Chile, the Vera C. Rubin Observatory is preparing for a different kind of marathon. Every few nights for a decade, its enormous mirror and giant camera will scan the entire southern sky, not once but over and over. This legacy survey of space and time will not be a static snapshot. It will be a movie of the cosmos, detecting billions of galaxies and tracking how their brightness changes. This dynamic view will allow scientists to catch fleeting cosmic events and, crucially, to measure the redshifts and positions of galaxies with incredible statistical power, filling in the cosmic web map with more points of light than ever before. Together, these projects represent a coordinated journey into the unknown. They will measure the growth of the web's structure, track the expansion of the great voids, and weigh the invisible halos of dark matter with a precision that was pure imagination just a generation ago. The data will be a torrent, a flood of information so vast it will require new branches of artificial intelligence to sift through and find the patterns. This is not just about adding more dots to the map. It is about watching the map itself evolve, frame by frame, across the history of the universe. We are about to see the cosmic web not as a still image, but as a living, breathing entity, and in its motion, we may find the clues that rewrite our understanding of reality itself. The universe's grand design was not always so sharply defined. Like a photograph developing in a darkroom, the cosmic web emerged slowly from a smooth, faint beginning. In its youth, the universe was a far more uniform place. The ripples imprinted by inflation were there, but the contrast was gentle, the hills shallow and the valleys wide. The dark matter scaffold existed, but it was a ghostly, low-contrast version of the intricate lacework we see today. Gravity had only just begun its patient work of sculpting, gathering material from the smoother surroundings and channeling it toward the denser seeds. If you could have viewed the cosmos 10 billion years ago, the web would have appeared more like a faint, wispy haze, its filaments broader and less distinct, its nodes smaller and less brilliant. This transformation is not a guess. We can watch it happen by using the universe's own time machine, light itself. When astronomers point their telescopes deep into space, they are also looking deep into the past. The light from a galaxy 5 billion light-years away shows us how that galaxy and the web around it appeared 5 billion years ago. By systematically observing the universe at different distances, and therefore different epochs, scientists can assemble a flipbook of cosmic evolution. They measure what is called redshift, the stretching of light's wavelength caused by the expansion of the universe. A higher redshift means we are looking further back in time. By conducting massive galaxy surveys at various redshifts, astronomers can compare the cosmic web's anatomy across the ages. They ask precise questions. How clustered were galaxies 7 billion years ago compared to now? How thick were the filaments? How large were the voids? The answers paint a clear picture of growth. Over time, gravity's relentless pull amplified the initial contrasts. Matter steadily drained from the vast, underdense regions, flowing along the gravitational highways of the filaments and into the waiting nodes. The voids grew emptier and more expansive. The filaments, once diffuse rivers, became more defined, their galactic beads pulled into tighter, brighter strands. The nodes, the great clusters, ballooned in mass and brilliance as they consumed this incoming material, often through dramatic mergers with other clusters. This historical record is our most powerful test for the entire story of cosmic structure formation. The sophisticated computer simulations that grow virtual universes must not only produce a web that looks like today's. They must also accurately reproduce how that web looked at every stage in its past. When scientists run their simulations and then compare the virtual web at a redshift of 2, for example, to the observed web from that era, the match has to hold. It is a check on our understanding of gravity, dark matter, gas physics, and the influence of dark energy across cosmic time. The evolving web tells the definitive story of maturation. It chronicles the universe's journey from a nearly smooth, hot beginning to the magnificently complex and clustered state we inhabit today. Each snapshot is a chapter, revealing how the gentle whispers of the Big Bang grew, under gravity's patient guidance, into the great walls and cities of light we now map. This is not just history for its own sake. By seeing how the structure grew, we gain the confidence to predict how it will change in the eons to come, as the silent tension between gravity's pull and dark energy's push continues to write the future of the cosmic tapestry. This grand inventory of the cosmos contains a startling accounting error. For all our maps of galaxies and dark matter, we have somehow lost half of the normal stuff. The ordinary atoms that build everything we can see and touch, known to baryons, should exist in a specific, calculable amount based on the echoes of the Big Bang. Yet when astronomers add up all the stars in all the galaxies, all the cold gas clouds, all the planets and dust, the total comes up short by a staggering 50%. An entire half of the normal matter in the universe is simply missing from our ledgers. It is as if you carefully counted every piece of furniture in a mansion, but completely overlooked the walls and floors that give the house its structure. This is the missing Baryon problem, one of the most persistent and curious puzzles in modern cosmology. Where could an entire universe worth of atoms possibly hide? The leading suspect is not in some distant, unseen realm, but woven into the very fabric of the cosmic web itself. Theorists point to the filaments, those great dark highways connecting galaxy clusters. They propose these threads are not empty, but filled with an extraordinarily diffuse and searingly hot gas. This is the warm-hot intergalactic medium, or the WIM. Imagine a fog so thin it is almost a vacuum, but heated to temperatures of millions of degrees by the immense gravitational forces that shaped the web. Gas this hot does not glow in visible light. It does not form stars. Instead, it emits a faint whisper of X-ray energy and leaves subtle absorption fingerprints in the ultraviolet light of distant quasars, the same Lyman alpha forest we discussed earlier, but for highly ionized heavy elements like oxygen. Finding this phantom gas is a monumental technical challenge. Its signal is incredibly weak, drowned out by brighter sources and stretched thin across unimaginable volumes. It requires space-based observatories like XMM Newton and Chandra, tuned to see the soft X-ray glow, and instruments like the Hubble Space Telescope searching for those specific, faint absorption lines in quasar spectra. The hunt is a piecemeal detective story. Astronomers do not take a picture of a filament. Instead, they stare for days at a chosen region of sky where two galaxy clusters are connected by a suspected filament, patiently gathering every precious photon to see if there is an excess of X-ray emission tracing the bridge between them. Or they study the light from a quasar, looking for the telltale signatures of highly ionized oxygen or neon that would indicate their beam passed through a hot, diffuse cloud. Each tentative detection is a triumph, a few more atoms accounted for in the cosmic budget. The evidence is mounting that the WIM is real, and that it indeed holds a significant portion of the universe's missing normal matter. Successfully mapping this elusive component would be a final, profound step. It would complete our inventory of the ordinary universe, confirming that the atoms we are made of are not mostly lost, but are simply in a state we are only learning to perceive. They form the thin, hot atmosphere of the largest structure in existence, the breath within the cosmic skeleton. Finding them would close one of cosmology's great chapters, assuring us that we finally know where all the pieces of our tangible reality reside. This hot, thin plasma is the final frontier in our cosmic census. The warm, hot intergalactic medium, often called the WIM, is theorized to be the elusive atmosphere of the cosmic web itself. Imagine the space between galaxies not as a perfect vacuum, but as a ghostly searing fog. Its temperature is staggering, ranging from 100,000 to 10 million degrees Kelvin, yet it is so incredibly diffused that a single cubic meter of it might contain only a handful of atoms. For comparison, the air we breathe has trillions of times more particles in the same volume. This combination of extreme heat and extreme thinness is what makes the WIM so devilishly hard to see. It does not glow in visible light like a star, or even in the radio waves like cold hydrogen gas. Instead, it whispers in language of high-energy physics, emitting and absorbing only very specific, hard-to-detect X-ray wavelengths. This faint signal is easily drowned out by brighter sources, like trying to hear a single violin note in the middle of a roaring symphony. That is why hunting for this material requires the most specialized tools in astronomy's arsenal. Ordinary optical telescopes are blind to it. The demands space-based observatories like the Chandra X-ray Observatory and XMM Newton instruments specifically designed to capture these high-energy photons. Their work is a lesson in patience and precision. Astronomers do not simply point and shoot. They must stare at carefully chosen regions of the sky for days, even weeks, accumulating every precious photon of X-ray light. They often focus on suspected filaments that bridge two known galaxy clusters, places where theory predicts this hot gas should be funneled and slightly denser. The goal is to detect an excess, a faint but statistically significant glow of X-rays, tracing the invisible bridge between the luminous nodes. It is a painstaking process, like trying to map a faint watermark on a vast dark page by gathering the tiniest specks. Light finding the WIM is about far more than just solving an accounting puzzle, though closing the missing Baryon gap would be a monumental achievement. Mapping this hot atmosphere is critical to understanding the full life cycle of cosmic matter. This gas tells the story of how the universe heats up as gravity pulls matter into the filaments and nodes of the web. The gas falls inward at tremendous speeds, crashing into itself and heating to these incredible temperatures. It is the universe's way of recycling this hot plasma, may eventually cool, flow into galaxies and fuel new generations of stars, or it might remain suspended in the web, a permanent part of its energetic fabric. By learning to see the WIM, we are not just finding lost atoms, we are reading the thermodynamic history of the cosmos. Understanding how energy flows through the largest structure of all, and completing our picture of where we and everything we know ultimately came from, the architecture of the cosmos, may hold an even deeper layer of order. Woven through the great dark filaments of the web, alongside the hot gas and dark matter, could be immense magnetic fields stretching for millions of light years. These are not the simple magnets of your refrigerator, but cosmic force fields of unimaginable scale, threads of energy within the threads of structure. Their origins likely reach back to the universe's infancy, to chaotic motions in the primordial plasma that could have generated a faint seed magnetic field. Then, as the cosmic web itself took shape, these fields may have been stretched and amplified, much like pulling on a rubber band makes it tighter. The constant flow of ionized gas along the gravitational highways of the filaments, that searing hot plasma we call the WIM, could act as a dynamo, twisting and strengthening these magnetic lines over billions of years. If they exist, their influence would be profound. Magnetic fields can channel the flow of hot gas, affect how it cools, and even regulate the formation of stars within galaxies. They could act as a cosmic pressure, subtly resisting gravity's pull or guiding how gas from the filaments funnels into the waiting galactic nodes. This adds a fascinating new dimension to the web story. It is no longer just a map of where things are or even what they are made of. It becomes a dynamic blueprint of forces where magnetism plays a role in the very evolution of the galaxies we see. Detecting these fields, however, is a challenge that pushes our technology to its limits. Because the fields are so faint and diffuse, we cannot see them directly. Instead, astronomers must look for their subtle fingerprints on the light that passes through them. One method involves searching for a specific type of radio emission called synchrotron radiation. This is the light given off when high-energy electrons spiral around magnetic field lines. A faint, polarized glow of this radiation tracing a filament would be a telltale sign. Another technique relies on the Faraday rotation effect. As polarized light from a distant quasar or radio galaxy travels through a magnetized filament, the magnetic field gently twists the orientation or polarization of that light. By measuring this twist across many different lines of sight, scientists can begin to reconstruct the shape and strength of the hidden magnetic landscape. Discovering and mapping this cosmic magnetism would be a revolution in our understanding. It would reveal that the universe's largest structure is not a passive skeleton, but an active and complex system, threaded with invisible forces that have helped write the history of every galaxy, including our own. A galaxy's fate is written in its cosmic address. The immense filaments and voids of the web are not a passive stage, but an active, nurturing network that directly guides the life story of every galaxy within it. Think of a galaxy located along one of the great dark matter filaments, a luminous bead strung on that invisible thread. This is a privileged position. The filament acts as a cosmic feeding tube, funneling a steady, gentle stream of cool gas from the vast intergalactic reservoirs directly toward the galaxy. This fresh fuel settles into the galaxy's disk, condensing into vast clouds that eventually collapse to ignite new stars. For these galaxies, the web provides a sustaining connection to the raw material of creation, allowing them to flourish as vibrant, star-forming spirals, glowing with blue-white light from their brilliant young stellar populations. Now consider a galaxy with a very different address, one that has migrated into the dense, bustling core of a massive cluster at a node. Here, the environment is far more intense and transformative. The space between galaxies in these metropolises is not empty. It is filled with an incredibly hot, thin plasma known as the intracluster medium. As a galaxy moves at tremendous speeds through this superheated fog, it experiences a relentless pressure like a powerful headwind. This process, called ram pressure stripping, can remove the galaxy's own cool gas reservoir right out of its disk. Without this cold fuel, the galaxy can no longer form new stars. Its existing, older, redder stars remain, but the galaxy itself gradually changes from a blue, star-forming spiral into a smooth, red, and quiescent elliptical shape. Its star-forming life gradually concludes, leaving it a more passive resident of the crowded urban center. This fundamental contrast between the nurturing filaments and the demanding clusters reveals how the web's architecture dictates destiny. A galaxy's journey through this landscape further shapes its identity. Two galaxies traveling along the same filament may eventually be drawn close together by their mutual gravity, leading to a slow, majestic dance over billions of years. Their spiral arms stretch and distort, they may merge, their gas clouds colliding and triggering furious bursts of new star formation before settling into a single, new galactic form. These interactions are orchestrated by the web's gravitational pathways. Even a galaxy floating in isolation within a vast void tells a story defined by its location. Cut off from the nourishing flows of the filamentary network, such a galaxy must live on its own limited reserves of gas, often resulting in a quieter, more solitary existence. By reading a galaxy's place within this grand map, astronomers gain a powerful new lens. They can look at a distant, red elliptical galaxy and understand it may have once been a spiral that journeyed into a cluster long ago. They can see a blue spiral and know it is likely still connected to the web's vital flows. This connects the very largest scales of the universe, the architecture of dark matter and dark energy, directly to the fate of individual islands of stars. The cosmic web does not merely contain galaxies. It raises them, guides them, and ultimately determines the kind of cosmic citizens they become. The map we have drawn is incredibly detailed, yet it hints at whispers from something we do not fully understand. For decades, the prevailing theory of our universe, known as the Lambda cold dark matter model, has been our most reliable guide. It describes a cosmos dominated by dark energy, represented by the Greek letter lambda, and by cold, slow-moving dark matter particles that interact only through gravity. This framework has been spectacularly successful, predicting the general shape of the cosmic web, the patterns in the cosmic microwave background, and the accelerating expansion we observe. It is the foundation upon which all our magnificent simulations are built. But as our maps grow sharper, a few subtle, persistent anomalies have begun to appear like faint marks on a beautifully crafted lens. These are not failures of the theory, but intriguing puzzles that suggest our picture, while largely correct, might be incomplete. One puzzle lies in the profound quiet of the cosmic voids. According to the standard model, these vast empty regions should not be perfectly smooth. The gravitational influence of the surrounding web should have drawn a few stray dwarf galaxies or clouds of material into them over time, leaving a faint, textured quality. Yet some of the largest voids we observe appear surprisingly clear, almost too uniform. It is as if something has settled them into a state of greater simplicity than our simulations predict. Another subtle tension exists on the opposite end of the scale, within the dense neighborhoods of galaxies themselves. The way galaxies cluster together on relatively small scales, how they group into pairs and small gatherings, seems to have a slightly different statistical signature than what the Lambda cold dark matter model anticipates. The match is very close but not perfect. These discrepancies are minute, woven into enormous datasets, but they are consistent enough to make cosmologists pause and ask profound questions. Could the properties of dark matter itself be different from our cold assumption? The standard model treats dark matter as collisionless, meaning particles pass right through each other and through ordinary matter without a trace. But what if dark matter has just a tiny bit of interaction, a faint ability to nudge itself or even with the hot gas in the filaments? This self-interacting dark matter could explain the uniformity of voids, as the particles would scatter and spread out more evenly, like a gas finding its own level. Alternatively, perhaps dark matter is not completely cold but slightly warm, meaning the particles moved with a bit more speed in the early universe. This warmth would have influenced the formation of the very smallest structures, which could then alter how galaxies cluster on those smaller scales today. Each adjustment to the dark matter recipe changes how the cosmic web forms in a computer simulation, and astronomers are now running those alternative simulations to see if they can produce a web that matches our observed map more precisely. An even more foundational question is being asked. Could our understanding of gravity itself need reconsideration on the largest scales? The Lambda cold dark matter model rests firmly on Einstein's theory of general relativity. But what if gravity behaves differently over the immense distances between galaxies and clusters than it does within our solar system? Modified Newtonian dynamics, or MOND, is one such alternative proposal. It suggests that the effects we attribute to dark matter are actually caused by a change in how gravity works when its pull becomes incredibly faint, like in the outskirts of galaxies. While this idea has faced challenges explaining all the evidence, particularly in observations of galaxy clusters, the concepts behind it push scientists to consider all possibilities. The cosmic web, with its precise geometry and evolution, is the ultimate laboratory for testing gravity itself. By measuring exactly how fast nodes grow and how filaments stretch over cosmic time, we are conducting a direct test of Einstein's equations on a canvas spanning billions of light years. This is the true power of mapping the universe's skeleton. It is not merely an exercise in cataloging. It is a continuous, rigorous experiment. Every new, deeper survey, every more precise measurement of a filament's character or a void's nature is a data point that either confirms our foundational theories or gently guides us toward a new understanding. The persistent whispers in the data are not signs of failure, but invitations to a deeper discovery. They remind us that the cosmos is under no obligation to conform perfectly to our elegant models. The great web is out there, its structure etched in light and shadow, waiting for us to read it correctly. Any lasting difference between our map and our prediction is not an end, but a beginning, a potential opening to a new chapter in physics that could redefine the forces that shape everything. Our galaxy, the Milky Way, has an address within this immense cosmic architecture. We are not floating in some central, privileged plaza of the universe. We reside within one of its great filaments, a luminous thread in the grand design. More specifically, our home is part of a modest gathering called the local group, which itself lies on the fringes of a much larger structure, the Laniakea supercluster. Laniakea is a Hawaiian word meaning immense heaven, and it describes a gravitational watershed containing about 100,000 galaxies. Yet even this breathtaking supercluster is merely one node among countless others in the web. This placement carries a humbling and powerful message, a principle sometimes called the principle of mediocrity. It suggests there is nothing cosmically special about our location. We are not at the center. We are not in a unique void or an extraordinary cluster. We are in a perfectly ordinary neighborhood on an unremarkable filament within a standard supercluster. This realization, far from diminishing our significance, actually weaves us more deeply into the fabric of everything. It confirms we are a natural, integrated part of a coherent whole. This cosmic map connects us on a fundamental level to galaxies so distant their light has been traveling for billions of years. Every galaxy we see, from the brilliant swirl of Andromeda to the faint smudges at the edge of our telescopes, shares this common architectural origin. We all grew from the same subtle ripples in the newborn cosmos. The same dark matter scaffold shaped our local filament that shapes filaments 10 billion light-years away. The same laws of physics, the same gravitational choreography, arranged the stars in our night sky as it did in skies around planets we will never see. When we contemplate the cosmic web, we are not looking at something separate from us. We are looking at the extended structure of our own home, a home of unimaginable scale. We are inside the tapestry, and the threads that bind distant galaxy clusters also pass through our own region of space. This perspective fosters a profound sense of unity. The narrative written in the web's filaments is a story of shared origin. Every atom in our bodies, every element forged in stars, was once part of that smooth, early universe. It was pulled along these same gravitational currents, flowing into the galactic nursery that would become the Milky Way. The iron in our blood, the calcium in our bones, the oxygen we breathe, all traveled along the hidden pathways of the web to reach this place and time. In a very tangible sense, the universe is not just around us, it is within us. We are not merely observers of this grand structure, we are its conscious expression, a way for the cosmos to begin to understand itself. Therefore, mapping the cosmic web does more than satisfy scientific curiosity. It answers a deep human longing to understand our context. It shows us that isolation is an illusion of scale. Across the vast distances, we are linked by a common history and a shared framework, participants in a single, unfolding story that began with the first moment of time. Our place is not at the center, but it is a place of connection, woven into the very skeleton of existence. This knowledge transforms the night sky from a collection of lonely points into a map of kinship, reminding us that we belong to something far greater than our own world. The universe's greatest map is being drawn by millions of hands. When a telescope like the Sloan Digital Sky Survey completes its work, it does not produce a simple picture. It generates an immense catalog, a digital ocean containing the precise positions, colors, and shapes of hundreds of millions of galaxies. For a small team of professional scientists, analyzing this tidal wave of data is an impossible task. This is where a beautiful collaboration begins, one that invites the entire world to become cosmic cartographers. Projects like Galaxy Zoo harness the unique pattern recognition of the human eye, something computers still struggle with. Volunteers from all walks of life log on to view an image of a distant galaxy and answer a simple question: is this a spiral or an ellipse? Does it show signs of a merger? With each click, a volunteer is not just looking at a pretty picture. They are placing a single, vital data point on the map of the cosmic web, helping scientists understand how a galaxy's form relates to its address within the grand structure. Through the collective effort of hundreds of thousands of people, galaxies have been classified at a speed and scale that would have taken a small research team lifetimes. This public participation has led to genuine discoveries, like identifying entirely new classes of rare galaxies that automated software had overlooked. It proves that curiosity is a universal instrument, and when focused, it can help trace the outlines of existence itself. This spirit of open exploration extends beyond classification. The raw data from these monumental sky surveys are not locked away. They are published online, freely available to anyone with an internet connection. This means a student in a classroom, an amateur astronomer with a backyard telescope, or a curious individual anywhere on the planet can download the same celestial datasets used by the world's leading cosmologists. They can write simple code to plot galaxies in 3 dimensions, to search for patterns, or to test their own ideas about the universe's structure. This democratization transforms cosmic cartography from an elite endeavor into a shared human project. It allows for unexpected insights from fresh perspectives, accelerating the pace of discovery in ways no single institution could predict. More importantly, it fosters a profound and personal connection. When you personally plot the points that reveal a filament or isolate a distant cluster from the data, you are not just learning about the cosmic web. You are engaging with it directly. You become part of the ongoing story of its mapping, contributing to a collective understanding that transcends borders and backgrounds. In this way, the greatest structure in the universe also becomes one of our greatest tools for unity, inviting all of us to look up and help find our place within the immense and beautiful tapestry. The data from our telescopes is a language of numbers and coordinates, not of light and shadow. To truly see the cosmic web, we need interpreters, translators who can turn this abstract catalog into a form our senses can embrace. This is where the artist and the data visualizer step in, becoming essential partners in the scientific journey. Their canvas is not traditional, but digital, built from the same immense simulations that scientists use to test theories of the universe. They take the output of supercomputers, the positions of millions of simulated dark matter particles and galaxies, and they begin to sculpt with light and color. Their goal is not to create fantasy, but to reveal a hidden reality with artistic license. They must decide how to represent the unseeable. How do you give form to dark matter? How do you illustrate the intense energy of the gas in a filament? The solutions are both technical and profoundly creative. They might assign a soft, ethereal glow to the dark matter halos, making the invisible scaffolding suddenly appear as a delicate blue lace woven through the darkness. They give the energetic gas in the filaments a warm orange hue, turning them into great, luminous rivers of light. The voids become deep, resonant purples or blacks, emphasizing their profound emptiness. These decisions are guided by science, but executed with an artist's eye for composition and emotional impact. The result is a visualization that is not a photograph, but something perhaps more valuable, a guided tour of the data. We are flown along a filament, diving toward a brilliant cluster, then pulling back to see the entire web spinning in the void. These animations make the scale tangible. They allow us to experience the structure as a dynamic, three-dimensional entity, not as a static scatter plot on a scientist's screen. For the public, these visualizations are a gateway to awe. They transform an intimidating scientific concept into a direct sensory experience, sparking that innate wonder about our place in the cosmos. For scientists, they serve a different but equally vital purpose. A well-crafted visualization can reveal patterns and relationships in the data that might be missed in columns of numbers. It allows researchers to visually track the effects of adjusting a simulation parameter, observing how the web's form changes if dark matter behaves differently or if dark energy is stronger. In this way, art becomes a tool of discovery, a new way of seeing that benefits both the heart and the mind, making the grand architecture of the universe not just understood but felt. This grand cosmic architecture speaks a universal language of connection. The principles that sculpt the web of galaxies are not confined to astrophysics alone. They resonate across the entire spectrum of human knowledge. To truly comprehend the cosmic web, scientists are now engaging in a profound dialogue with fields as diverse as complexity science, network theory, and advanced data analysis. The universe's largest structure is being understood not just as a collection of objects, but as a dynamic, interconnected system, a network in the truest sense. In this view, each galaxy becomes a node, a point of intersection. The gravitational bonds between them, the invisible lines of force shaped by dark matter, become the edges, the connections that define the network's shape. By applying the mathematical tools of network theory, researchers can quantify the web's anatomy in new ways. They calculate properties like the clustering coefficient, which measures how tightly galaxies group together in local neighborhoods, or the path length, which describes how many connections lie between any two distant points in the cosmic net. These metrics reveal that the cosmic web is a highly clustered, small world network. This is a structure where most nodes are connected to their immediate neighbors, but where surprisingly short pathways can link even the most distant regions. This is an organizational pattern that appears again and again in nature and human society, from the neural connections in our brains to the relationships within a community. Mapping this network manually from billions of data points is an immense task for the human mind alone. This is where the newest tools of discovery come into play. Advanced machine learning algorithms trained on our best simulations are now set loose upon the real observational data. These artificial intelligences learn to recognize the subtle statistical signatures of a filament or the distinctive emptiness of a void. They can sift through terabytes of galaxy survey data, automatically tracing the web's delicate threads and vast chambers with a speed and consistency that surpasses any human team. This is not replacement but augmentation, allowing scientists to ask bigger questions of larger datasets than ever before. This cross-pollination of disciplines creates a richer, more vibrant understanding. It shows us that the universe, in its grandest expression, is not an alien or incomprehensible place. It operates on principles of organization, growth, and connection that we find echoed in the complex systems all around us. The same mathematical patterns that describe how information flows through the internet or how a community responds to a challenge can help us understand how galaxies influence one another across millions of light years. In tracing the cosmic web, we are not just drawing a map of outer space. We are uncovering a fundamental logic of connection, a universal grammar written in gravity and dark matter that helps to weave the tapestry of reality itself, from the vastness of the cosmos to the intricate networks of our own world. Our map of the cosmos has a final, unbreakable boundary. It is a frontier not of distance but of information, a horizon drawn by the very laws of physics and the history of light itself. We call this the observable universe, the vast but finite sphere of space from which light has had time to reach us since the beginning of everything. It is a bubble of knowability, and we are at its center not by privilege, but by the simple fact of our existence here and now. Within this bubble, we trace the cosmic web with ever greater precision. Yet we must confront a profound truth. The magnificent filaments and voids we chart are not the entire universe. They are only the part of it that is, and forever will be, connected to us by the messenger of light. This is the ultimate limit of our cosmic cartography. The most distant wall of this bubble is not darkness, but a wall of ancient light. When we point our most sensitive instruments to the edge of the observable universe, we do not see galaxies. We see the cosmic microwave background, that faint afterglow from when the universe was a mere 380,000 years old. Before that moment, the cosmos was an opaque, searing plasma, and light could not travel freely. The microwave background is the ultimate veil. It is the earliest snapshot possible, the glowing surface of the primordial fog. We cannot see through it. It marks the limit of our direct view, the ultimate boundary of our optical telescope. Any structure, any earlier chapter of the web's formation that existed before that time, is forever hidden from our direct observation, its details lost in the brilliant glare of creation's dawn. But there is another, more subtle horizon emerging in our future, one defined not by the past, but by the present acceleration of the cosmos. Dark energy's relentless push is stretching the fabric of space itself. As this expansion accelerates, galaxies that are already at the far edges of our observable bubble will have their light stretched to longer and longer wavelengths, eventually fading into undetectability. More crucially, the space between us and those distant regions will eventually be expanding faster than the speed of light. When that happens, any new light they emit can never reach us. They will have passed beyond our cosmic event horizon, slipping out of the observable universe forever. Over eons, our island of knowable space will shrink, not grow. The grand, connected web we see today will slowly unravel from our perspective. Distant filaments will fade, and brilliant clusters will wink out of view, not because they vanish, but because the connection is severed. The universe we are mapping so diligently is a temporary gift, a snapshot of a specific era when the cosmos is still transparent enough for its largest structures to be seen. This realization defines the ultimate scope of our knowledge. The cosmic web we trace so carefully is a finite chapter in a story that may be infinite. What lies beyond our observable bubble? Does the web simply repeat with variations, stretching on forever in a pattern of filaments and voids? Or does it give way to entirely different geometries, realms governed by different physical constants? We have no way to know, and likely never will. The data we gather, the breathtaking maps we create, are confined to this one magnificent sample, this one connected piece of the whole. This is not a failure of science, but a clarification of its domain. It teaches us humility, framing our entire epic quest for understanding within a natural, physical boundary. Yet within that boundary, the work is more urgent and meaningful than ever. This finite map is our only direct connection to the totality of existence. Every galaxy we plot, every filament we trace, is a piece of the universe that is, for now, in conversation with us. It is the part of the cosmos with which we share a causal history, linked by chains of light and gravity stretching back to the Big Bang. By studying this accessible web, we are learning the universal rules that likely govern all of reality, even the parts we can never see. Our map, for all its limits, is the key to the infinite. It reminds us that we are not just mapping the universe, we are mapping our home, the only neighborhood of reality we are ever guaranteed to know. The universe's grandest structure and its tiniest rules share a secret origin. Our journey from the quantum realm to the cosmic web is perhaps the most profound narrative in all of science, a story where the very small writes the script for the very large. Those initial seeds, the microscopic ripples in the newborn cosmos, were quantum fluctuations, random flickers in the energy fields that filled the primordial expanse. Inflation, that moment of hyper-accelerated expansion, did not create these ripples, but it magnified them, stretching those subatomic wrinkles to scales spanning light years. This means the specific pattern of hills and valleys imprinted across the infant universe, the blueprint for all future structure, was born from quantum uncertainty. The delicate lacework of the cosmic web is, in its deepest essence, a quantum pattern grown to an immense scale. This profound connection turns the detailed map of the web into something far more significant than a cosmic chart. It becomes a testing ground for our most ambitious theories of reality. The ultimate goal of modern physics is a single framework that seamlessly unifies the two pillars of our understanding. On one side, we have quantum mechanics, which describes with stunning accuracy the behavior of particles and forces at the smallest scales. On the other, we have general relativity, Einstein's masterpiece that describes gravity and the large-scale structure of spacetime. These two theories work perfectly in their own domains, but they are fundamentally incompatible. They speak different mathematical languages and break down when forced to describe the same event, like the center of a black hole or the first instant of the Big Bang. Bridging this great divide requires a new physics, a theory of quantum gravity. Several candidates exist, each proposing a radical reimagining of spacetime itself at the most minute scale imaginable, a distance so tiny it is a billionth of a trillionth of the size of an atom. We cannot build a particle accelerator powerful enough to probe these energies directly, so we must look for the indirect cosmic fingerprints these theories might have left behind. This is where the cosmic web enters the quest. If the seeds of the web are quantum in origin, then the precise statistical properties of the web today could carry subtle imprints of the quantum gravity processes that operated during those first moments. It is like trying to understand the properties of a single grain of sand by studying the vast desert dune it helped to form. Researchers are now asking exquisite questions of our maps. Does the web show any faint statistical deviations from the standard predictions that more complex unified models might produce? Are there any unexpected correlations or patterns on the very largest scales that hint at spacetime having a discrete, granular structure at its foundation? By comparing the predictions of these advanced theories against the exquisitely detailed observational data from galaxy surveys, we are conducting an experiment of cosmic proportions. We are using the universe itself as our laboratory and the cosmic web as our most sensitive instrument. In this endeavor, mapping the architecture of the universe transcends astronomy. It becomes fundamental physics. Every filament we trace is not just a river of galaxies, it is a line of evidence. Every vast void we measure is not just an empty space, it is a window into the quantum nature of reality. By linking the infinite to the infinitesimal, we are not just finding our place in the cosmos, we are deciphering the very code from which it was built. The cosmic web is a story of profound connection written across the emptiness. Our journey through its filaments and voids reveals a universe of breathtaking order, a vast architecture woven from dark matter and traced by the luminous cities of galaxies. This structure is not a static monument, but a living history, born from quantum whispers and sculpted by the slow, titanic dance between gravity's pull and dark energy's push. It is the ultimate expression of cosmic design, the final shape of everything that has unfolded since the first moment of time. To map this web is to engage in one of humanity's greatest scientific endeavors, a quest that stretches the very limits of our technology, our imagination, and our understanding of physics itself. It pushes us to build telescopes that act as time machines, to write code that grows entire universes inside supercomputers, and to forge new tools of thought that bridge the infinitesimal and the infinite. This map is far from finished. As a new generation of observatories like Euclid, the Roman Space Telescope, and the Vera C. Rubin Observatory come online, our chart of the cosmos will transform from a rough sketch into a hyper-detailed atlas. We will watch the web's evolution across billions of years with unprecedented clarity, studying the invisible dark matter framework directly and measuring the subtle imprint of dark energy's accelerating influence. These new vistas promise to solve enduring mysteries, like the final location of the universe's missing ordinary matter, and to rigorously test the fundamental laws we believe govern reality. They will likely reveal new puzzles, unexpected wrinkles in the data that guide us toward deeper truths, perhaps even toward a new understanding of gravity or the nature of the dark universe itself. This pursuit connects us all, from the professional scientist analyzing vast datasets to the volunteer classifying galaxies online. We are collectively learning to read the universe's grand design. And so, the next time you find yourself beneath a clear night sky, remember you are not looking at a random scattering of isolated points. You are gazing at a single, luminous thread in a magnificent, ever-growing tapestry. You are seeing the local expression of the largest structure in existence, a structure that connects every galaxy in a shared story of origin and destiny. If this exploration of the universe's hidden framework has captivated you, consider subscribing for more journeys into the heart of cosmic mysteries. We would love to hear your thoughts on this vast web, so feel free to share your reflections in the comments below.